of systems. Okay, so as I have given a brief introduction to control system in the last class, I mentioned a few words about systems. That what is meant by a system, what is the difference between the different nomenclature that we use, that is plant, process, and we found out that we have discussed that system basically encompasses plant, process, or it can be thought of as anything that we intend to control, or we intend to study, or we intend to use or observe. So it may be a physical system, or it may be a non-physical system, it may be a hypothetical system as it maybe also. So let us start with the basic definition of system. So how do we define a system? See, we'll start at first from a very broad point of view, then we'll concentrate on what a system is from an engineering point of view. To start with, what is the definition of a system? A system is regarded as a quantitative description of a physical process. Obviously, it's a from engineering perspective, you can see there is physical process that transforms signals at its input to signals at its output. Now, the key word that you should give emphasize on here is a quantitative description. Okay, since from an engineering or from a analysis point of view, we need quantitative description. That is, a qualitative description will not be sufficient to define or to describe a system. Okay, what is qualitative? Qualitative means you say it's a good system, its performance is good, its performance is not satisfactory. That doesn't qualify as a description because you're not specifying how good it is or in which respect the performance is satisfactory. What are the parameters or the indices that you are talking about? So a system can be thought of a quantitative description, not a qualitative one. Of what? Of a physical process. Now, physical process, it may be a physical process, it may be a physical plant, or it may be anything which has an input and an output, and the description, the quantitative description, should define the transformation that causes the system causes on the input signal to transform it to an output signal. That is how it transforms the input signals to output signals. So if you look at from a mathematical abstraction, a system can be more precisely thought of a black box. Okay, we do not know what is inside the system, and we only know that given a particular input, it produces an output. And to define a system, or whenever you study a system, we should be able to deterministically find out this transformation. Or in other words, a system is regarded as a black box that deterministically transforms the input signals to output signals. That is, it is not a random, it is not something vague or qualitative, it's a quantitative. And this transformation, you can determine, you can express this transformation in terms of some mathematical expression. Okay, that is why it should be a black box that deterministically transforms. Here, the keyword is being deterministic. Okay, next. So, from a physical point of view, you can thought of a system from a very layman's point of view, a set of interconnecting or interdependent components, right? Or different parts that act together and completes completes a set of equipment or set of tools that performs a complex or a very dedicated task. So, whenever you're discussing system, we should first be able to identify a system, that this is our system. And how do you identify a system, or how a system can differentiate itself from others? A particular system, how it differentiates itself from others. That is, every system is delineated by its spatial and temporal boundaries. That is, every system will have a spatial boundary. That is, it is occupying this much of space, and temporal boundaries, because in some situations the system may have some time dependence. So it will be varying with respect to time. And so it should be clearly delineated in terms of its spatial presence as well as temporal presence. The next question comes, if that is so, then what is the surrounding? Whenever you delineated a system, delineate a system, then it is obviously surrounded beyond its boundary by what is called an environment. And not only the environment surrounds the system, it also influences the system. So you can say every system is surrounded and influenced by its environment. And this is a very key aspect, because whenever you have identified or segregated or delineated the system from its boundary by its boundaries, then rest of the thing is the environment. And if we ignore the environment completely, then we might be missing out on some key aspects of a system. That is, this environment is not merely there to fill up the gap, but it also influences the system in different manners, right? Like it produces some disturbances. The environmental condition may affect the system performance. Like, see, in a winter situation, some system may behave in a certain fashion. In very hot and humid summer situation, it may behave in some other situations. So whenever we specify a particular system, we have to specify the temperature range or the environmental condition as well under which the system is performing. So that is very important. You should not only identify the system and its environment, but should also consider how the environment influences the system. Then every system is described by its structure, that how the system is developed or designed or realized, and the purpose, the very purpose the system serves. And function, finally, it is expressed in terms of its functioning, how the system is functioning to fulfill the purpose or serve a particular objective. So these are the key aspects that will help us to identify a particular system which we want to study or analyze. Next, in continuation with this, you can say a physical system. Now we are coming back to the physical system, to be very precise. It's a collection of physical objects that we have already discussed in the last class, and this purpose is to solve a particular objective. Now, example of physical systems I have given already, starting from a very basic electronic amplifier to the satellite. So you can say anything under the sun that you intend to study or use to serve a particular purpose or to achieve certain goal can be termed as a physical system. But in more general perspective, the word system should be used to describe not only a component of physical objects or a cluster of physical objects or tools, it also encompasses some economical, social, management system, educational system, right? These are also some systems that we regularly observe. We take feedback from the systems, we study the systems, and try to incorporate new changes to make the system behave in a desired manner so that it satisfies the very purpose of the system. So there, the system theory or the control system is equally applicable not only for the physical systems but also for this non-physical systems. And nowadays it finds its application more profoundly in these non-physical systems as well. So it is not only restricted to machines, tools, and complex operations of different industrial processes, but it also involves the study of economical, social, and management systems, educational systems as well. Now let us, once we have identified the system, now we have to need to classify the system. That before we study or start analyzing a system, we should be able to classify the system into different sectors, so that we follow a particular well laid out plan or well laid out method of analysis for that particular class of system. Each and every class of system has its own path of analysis. A single or unified path of analysis for all the systems is not that common. So how do we classify system? Let us see. First classification is continuous time system and discrete time system. So I guess this is a very trivial classification. Continuous time system means the system signals, that is input and output, are present continuously. That is, they are a continuous function of time, and the system acts on the input signal continuously, that is in continuation with time, and generates an output which is again a continuous function of time. On the contrary, in a discrete time system, the system is excited only at discrete intervals of time, and the system generates the output signals at discrete intervals of time. So there is a clear distinction between a continuous time system and a discrete time system. So go in details about that. Another classification will be linear system and nonlinear system. I guess this is all of you might be very aware of the fact that linear system means it follows the principle of homogeneity and superposition, whereas a nonlinear system which may fail to comply to either of them or both of them, that is homogeneity or superposition, will be termed as a nonlinear system. We'll go in detail about that. So any system that we want to study may be classified as a linear system or nonlinear system by checking whether they follow this principle of superposition or homogeneity or not. If they do so, there is a linear system. If they fail to comply to any one of them or both, there is a nonlinear system. Next, very important, we have a time invariant system and time varying system. Go in details about each and every classification in today's class. So time invariant system means the components present in the system are time invariant. Or you can say, if you give an input at any instant of time, the system will react to the input in a same manner. It doesn't depend on the instant at which you are giving the input signal. It will behave in an identical manner. On the other hand, the time varying system may behave in different manner depending upon when you are giving that particular excitation. Say for human body is basically a time varying system. See, when you are at peak of your awareness, that is once you get up in the morning, get freshen up, and you are full of energy, then given any task, or you're attending a class, say at 10 a.m class or 10:30 a.m class, you have just shrugged off your uh, lethargy and you've come to the class, then you'll be very very active, you'll be very proactive in the class, you'll be understanding the lectures very easily because your brain is at peak. Once you have taken the lunch break and you have taken sumptuous food, the first class after the lunch break seems very very difficult to attend, right? Because you are feeling very sleepy, because your system dynamics has changed. You're again gone into the lethargic mode. Then if you, some of you may recover in the third or fourth or period, say 3:30 4:30 period, there you may be aware. But if you have to attend a class at 8:30 at 9 or 9 p.m in the evening, after the day long phase of class, play, more fun, then you will be at a state where your intake capacity or enthusiasm will get very low. You will not be able to complete a task as efficiently as you could have done in the morning when you're at the peak of your energy level. So that is how a time varying system works. So given a task at any instant of time, if it's time invariant, say as a robot, if a computer, whenever you try to program a computer, whenever you give you a particular input, it produces the same output. There's no difference in it. Okay, other than if you have a very old system, or if you are doing overdoing with a computer, it might crash. So that is not a scenario. In ideal situation, in a normal situation, whatever input you give at whatever time, it will give you the same output, right? But for human being, it may not be true. Just like robots give whatever time you give an input, it will give you the same output. It doesn't have any fatigue or anything. So it's a kind of a time invariant system. I'll go in detail that why it is a time invariant and why it is time varying, because you can see or you can think of it as if the components present in a time invariant system are time invariant. There is no variation in the component values. Whereas in a time varying system, the components itself are time varying. Their values are changing with respect to time. That is why at different instance of time, you're getting different types of responses. So this is a very clear distinction of system, whether time invariant or time varying. Next, we have a very interesting classification: causal and non-causal system. Causal system means it behaves in a cause-effect manner. That is, whenever some input is given, then only based on that particular input or some past value of input, it generates its output. That is, cause have occurred, then as an effect, the output has changed. It has developed or it has generated an output. It's causal system. As you can think of, any physical system is basically a causal system. Then what is a non-causal system? A non-causal system may be something where the output is generated even before the input is come. So that is very difficult to apprehend, right? That how a system output can depend or can be generated based on some future input. Right? That is a definition of a non-causal system. I'll come in detail about all these points. Next, we have a most important classification, that is stable system and unstable system. Stable system means given a system, if you give a bounded input, if the system output is also bounded, or given an excitation, if the system comes to an equilibrium point, then you call it a stable system. But if a system given an excitation, it never comes to an equilibrium point, then it's an unstable system. Or given an excitation, a bounded excitation or bounded input, if the system output is not bounded, then you call it a unstable system. So there's a clear distinction, and obviously you can easily apprehend that in physical system, all the physical system, what we desire is a stable system. So we need to identify which system is stable and which is unstable. Then what to do with the unstable system? That will be our task. Given an unstable system, we'll study how to stabilize the system via designing a control system or a feedback system or any kind of a control system. That is the task of the control engineers. Given a stable system as well, there may be some task of control engineers to make it behave in a satisfactory manner because its performance may not be satisfactory. Then also you can use control system technologies or techniques to make it behave in a satisfactory manner. So these are the different classifications. Now let us discuss these classifications one after another. First, continuous time system and discrete time system. So it's the simplest and the most obvious classification to understand because the concept of discrete time and continuous time is very fundamental of any signal, and that is well applicable to the systems as well. So any physical system that we normally encounter is a continuous time system where the input and output signals are always present with respect to time. There is no discontinuity. Whereas in discrete time system, the inputs are available only at discrete intervals of time. Like in a practical situation, whenever you're dealing with a digital computer, then even if the we have a suppose we have a digital computer in a control process, a process control, then the analog signals are coming as an analog fashion, that's continuous with respect to time. But the digital computer will then discretize the signal and will act on the discrete intervals of signal, not on the entire signal. So if I try to discuss that in detail, so continuous time signal means system means given a sorry given a system, suppose the input signal is coming over here, and the nature of the system's input is time, and the corresponding output signal is coming over there, and the nature of the output is, then you call this a continuous time system. On the other hand, in discrete time system, what you have, here we have input signals. If you consider time to be axis, then we have signals that are present only at discrete intervals of time, and the corresponding output that it generates are also present in discrete instance of time, not always present there. So this is a clear distinction. Now, in physicality, since most of the systems are analog or continuous in nature, what we encounter is a hybrid system. How it is defined then? Suppose we have an analog signal, say RT. The nature of the signal is something like this. Then what you normally do, we use a sampler and hold, say a DC converter, analog to digital converter, and that converts the signal to, say, instant. It's not normally written in terms of t, but rather the sampling instance 0 t 2t, that is a, and there is a hold circuit. So it samples the values at different instants of time. It is at 0 instant, this is the value. At t instant, this is the value. So generates a signal like this, which is obviously a discrete time signal, say RKT, which is fed to the system, digital computer, and output of the digital computer will be again a discrete time signal. Now it is converted a digital to analog converter to a signal YT, which is again continuous in time. So it may not be like exactly like this. It may be like use different type of hold circuits. So it will be like either in the form of a staircase or like this. So this kind of a system, see here we have a continuous time signal as an input to the system, and a continuous time system signal as an output to the system. But intermediate we have discrete time or sample data system signals. So that is why it is called a hybrid system, where both continuous and discrete time signals are present, and you can say it handles both continuous time signal and discrete time signal simultaneously. That is why it is called a hybrid system. And we have different techniques of analyzing such systems. Okay, for discrete time system we use what is called Z transform technique, and for continuous time system we use normally a Laplace transform technique for analysis. That we'll discuss. Have you heard of Z transform? Anybody?
Yes, sir.
Okay, in your do you have a DSP in your curriculum? Where have
Uh,
you heard it?
Sir, from mechanical side, in our mathematics class, we have Fourier transformation, Z transformation, and Laplace transformation actually.
Okay, very good, very good. Fine. That is not in a syllabus, but still it's very, whenever you're talking about discrete time system you should have an idea, or you should at least know the name Z transform. Now the next classification, linear and nonlinear system. I think this is the most trivial of the classifications. So a linear system is that which obeys the properties of scaling and superposition, and a nonlinear system is a system which doesn't obey at least one of them or both. So let us take an example of a system H. Say it obeys the scaling property. Then what does that mean? That means given an input ft, if the output is hft, then given an input k of ft, the output will be k h of ft. There is a scaling property. If the input is multiplied by k, the output will also get multiplied by k. Similarly, to demonstrate how a system obeys a superposition property is that if it produces an output hf1t for an input f1 and hf2t for an input f2, then if you give an input f1 plus f2, then it would produce an output that is a summation of these individual inputs, right? The output with respect to the individual inputs. So these two property can be augmented to represent like this. That is, given an input k1 f1 plus k2 f2, the output will be K1 into output due to F1 plus K2 into output due to F2. So if a system satisfies this condition, then it's a linear system. It follows the scaling property and the superposition property. But if a system fails to satisfy either of them, either scaling or superposition or both, then it's a nonlinear system. We'll give an example of each and every system today. So this is a clear classification. It's a binary classification, you can say. Then time invariant and time varying system. So a time invariant system is one that doesn't depend, the response of which doesn't depend on when the excitation is given. Okay, the shape of the output, the nature of the output is invariant whenever the input is given. On the other hand, this can be represented as, suppose you have given an input ft, the corresponding output is h of ft, say yt. Now, if it is time invariant, then given an input h f of t minus capital T, that is, if it is delayed by an amount of capital T, then output will be delayed by the same amount while keeping the same expression or the same type of nature. Then you call it a time invariant system. But if it fails to ensure this property, then you call it a time varying system, right? How do you define? Let us take an example. I'll take two systems, and suppose this is your input, a step input I'm giving, otherwise zero, step input. Now, say for the first case, system one, when the step input is given at this time, the response is something like this. And here also, the response is something like this. Now, if we shift the input by an amount capital T, any amount capital T, in both the cases, is being shifted by amount 0, this is T, the time axis, and this is your 0, this is T. So now this signal is shifted by T. So initially the signal was ut, and now we have given a system u t minus t. Now under that condition case, if the response identical, so if this is yt, this is y of t minus t. But in this scenario, if the output response becomes, so this is y1 t minus, sorry, t, and this was y of t. So clearly, given an input ut, in this case it produces an output yt, and ut minus t produces an output. There is a same output shifted by an amount which is equal to the same amount by which the input is delayed. But in this scenario, ut produces yt, but u of t minus t produces another function which is not equal to yt minus t. So obviously this is a time varying system, and this is time invariant system. Understood? How do you define a time invariant and time varying system?
Yes, sir.
How do you understand this? So the main cause, that one of the major causes of for based system being time varying, is that if it has a parameter that changes with respect to time. So depending upon at which time you're exciting the system, the output will be depending on the value of that parameter at that particular instant of time. Okay. So next, coming on, we have causal and non-causal system. So what is a causal system? A causal system is kind of a non-anticipative system. That is, it acts on the cause effect nature of law, or nature or law. That is, the output can only depend on the present input or past input, but it doesn't depend on any future input. Okay, it cannot anticipate any input and act accordingly. So once the input has come, then only it will react. Cause effect kind of thing. So as you can easily apprehend that all real-time systems are causal, because you do not have any future input available at present time. Obviously, it is not possible. So the next question comes then, how, why we are discussing this non-causal system? Non-causal means the output at particular instant is a function of a future input. And once we are terming an input as a future input, then it cannot be present at the present time, right? Whatever input is present now is a present input. So you, in real time, as if it seems that we cannot have any future input, right? So then, why are we bothering about the definition of non-causal system? Can you think of anything which is a non-causal? It's very difficult. Actually, if you take time as an independent variable, as we normally do, then every system is a causal system, right? But if you change your perspective and take something other than time, say space, as your independent variable, then the non-causal system may be there. For an example, some of you are familiar with image processing, right? Once you have captured a digital image, what you normally have is the data. And what is the data that you have? Suppose this is in horizontal axis and this is a vertical axis. So say the number of pixel is 100 by 100. So you have a 100 by 100 image that you have captured, a digital image that you have captured, and that is stored in your memory, right? Now you're trying to analyze the system or trying some mathematical operation to say denoise the system or to enhance the quality of the system, okay, or to identify a particular feature of the system. So normally, what is one of the approaches of doing so? You select a vertical line and come encompassing from 0 to 100 in a vertical direction, that is in y-axis, and now you shift this line to the right, starting from x equal to 0 to x equal to 100, and at each and every point it's moved continuously. Suppose you measure the value or the RGB values of the particular pixel along the particular y-axis, right? So that is how you move along. Suppose at any instant of time you are at here, say location 30, and you are measuring all the corresponding values of y along this line, or the pixel values. So, and in the process you've encountered a, you're trying to figure out how this curve may end up, this line you're trying to figure out, because you do not know, it may end up like this, it may end up like this, it may end up taking a complete like this. So there may be different possibilities. And what you are trying to do, you're trying to linearize or produce a small segments like this, so that you can linearize it. The line can be piecewise linearized or try to extrapolate that. So at this point, you know the previous value, so you can just connect them by a straight line. Fine. Now at this point, you know whether you should continue with this straight line or the slope may change in different directions. So to anticipate, to get the value or whether there is a change in slope or not, what you require is another data, and that data you can retrieve from, say, the next pixel location x equal to 31. So and here you find that the point is now lying at this point, next line. So you know this is a segment, so you have to connect this line. So accordingly, you put up this point so that it can match the next line. So at this point, while joining these 2 points, you're not sure whether how it will move beyond this point. So having this data will help you in determining the nature of the line that you're drawing over here. So, but this data corresponds to a location x equal to 31. But we are now drawing up to x equal to 30 based on x equal to 29. This is a previous data, fine, this is a causal. But this x equal to 30 is something coming from the future, right? So this kind of operation where you're relying on some future data or future input to obtain the value or the nature of the curve at this point x equal to 30 is a non-causal operation. And your operation is dependent on a future input that is at x equal to 31. So this is a very simple example of non-causal system. And how it is possible? Because we are not dealing with some time as an independent variable. Rather, we are dealing with some value or data that is already stored. Here, the data is the value of the pixel RGB values at different location along x-axis and y-axis. And we are transcending along the x-axis and measuring the value of pixel along the y-axis. So at x equal to 30, to draw the line from 29 to 30, we are relying on data which is at x equal to 31. There's a future input. So that is why this non-causal operation is present in practicality. That is why this classification is there, causal and non-causal. Right? Can you think of anything like this that normally happens that may not be this much vivid or this much mathematical, but there is some non-causal operation that we normally our mind is used to act like. Can you think of any such thing? Non-causal operation? Any idea? Where you do not have the input, but you may have what you may have a prediction, or you may have some idea, and based on that you react. There may be a couple of examples like we used to navigate on Google Map, right? And while navigating, Google Map gives you the information about the traffic condition and possibility of traffic jam. It gives you warning, the possibility of traffic jam at a road ahead. And in that case, we have not yet faced the traffic jam, but we decide that we try to avoid, will avoid that road, right? So that is one kind of a non-causal operation. Obviously, in that case, we are anticipating. Our brain is anticipating based on the prediction. We have not faced the situation, but we are avoiding the situation. That's kind of a non-causal operation, right? We have intermediate thing. Another thing is that based on weather prediction, some events are avoided, some events are cancelled based on event weather prediction, because we know there's a prediction of heavy shower. Some events are postponed or they are cancelled because of that. Or we normally when you predict, normally now the weather department has become much more accurate, not unlike previous years. They normally give us quite correct predictions. So in that case, if we have a prediction that there might be rain, so even if we are getting out of the house in a very sunny day, we'll bring our umbrella. So when it rains, we are ready for it. So that process of thinking is kind of a non-causal. We are not yet faced the situation, but in anticipation, we are taking the step. We are giving a response, right? And there's another classification which is much more like a binary. Like causal system, the output depends on present and past values of input. For non-causal system, the output depends also on the future. That is, the output is dependent on present, past, as well as future. That's non-causal system. And there's another classification, anti-causal system, where the output depends only on the future values of input. Okay, not on the present or past value. This is the anti-causal system. Just a second. So can you think of any anti-causal method that you have used? Anti-causal example of anti-causal system? Yes. Anybody? It's related to mathematics. Or not k plus 1. Normally we use not like this. You can think of this as, right? And this is obviously this is a non-causal, and causal one will be right. See here the output or the this value at t, dx slope is a function of future, right? So it's a non-causal operation. Future and obviously the present input. So it's a non-causal operation. Agreed? But this is a causal. This is also present and this is past, right? But luckily, in most of the physical scenarios, we encounter basically causal systems. All the real-time systems are causal in nature. Next, stable and unstable system. A stable system is something where given a bounded input, we get a bounded output. That is, the output doesn't diverge, rather, it converges to a value, or in some situations, it may oscillate, right? But it doesn't diverge. And whenever a system excited by a bounded input gives an output which is also bounded, we call that system to be bivostable. So a stable system must have the following property. What is that? Given an input xt, which is bounded by some finite margin mx, the output must also be bounded by a finite margin my. Then only you can say the system to be bivostable, right? And if it fails to do so, that is, if the output grows without limit or diverges, and yt is not bounded by my, even though xt is bounded by mx, we call it an unstable system. We'll take example of each and everything. Now, before coming to the properties of the system, if we come back to the slide where we are discussing about the different types of system, there's a very important, interesting conclusion that we know a system can either be continuous or discrete. It can either be linear or non-linear. It can be time invariant or time varying. It can be causal or non-causal. It can be stable or unstable. The only thing is that for continuous time system and discrete time system classification, there may be some gray areas where we use to have hybrid system. In discrete time system, it may be pure discrete time system or hybrid system due to the presence of continuous time components or continuous time signals. So, if you want to classify a system, it may be classified as, say, a continuous time. Then that continuous time system may be linear or non-linear, not both at the same time. So a continuous time system may be linear or non-linear. Say it's a linear system. Say then that continuous time linear system may be time invariant or it may be time varying, right? Similarly, continuous time nonlinear system may be time invariant or time varying. A discrete time system may be linear or non-linear, so that may be time invariant or time invariant. So this is like a branching. So there may be numerous permutations and combinations that you can have. So let us say the linear system, continuous time linear system is time invariant. Then that this system may be causal or non-causal. Then let us consider that to be causal. And finally, this system may be stable or unstable. So for our case, we consider that to be a stable one. And that is not the every classification that you can have. You can have, as you've understood, either continuous time or discrete time, either linear or non-linear. Here, there may be some gray area due to the presence of hybrid system, but still, the rest of them are binary. So a system can satisfy either the left half or the right half of each and every classification. It cannot simultaneously be linear or non-linear. If it is non-linear, it can never be linear. If it is time invariant, it can never be time varying. Right? So that is why if you select any one from each and every row, you have to stick to it. So in our scenario, in our analysis that will follow, we'll consider continuous time, linear, time invariant, causal, stable system. Or in a sense, linear, time invariant system. This LTI is a very common term. Linear time invariant system, which is continuous time as well as causal and stable. Right? So we shall only concentrate on this class of system. Okay. Let us proceed with the properties of the system. Different properties that a system carries. First property is a system having memory or not, whether a system has a memory or not. That means if the system is memoryless, if the output at any instant depends on the input at that instant only. On the other hand, if the output at particular instant is not only function of input at that instant, but also a function of the output or the input at previous instance of time, then we call the system to have memory. A simple example, see, this system is a memoryless system because at any instant t, that output yt is a function of input at that instant only. So it's a memoryless system. In a discrete time system where it is represented as a sequence of output and yn and the sequence of input xn, it is also memoryless because at any instant of time n, the output is equal to the input at that instant. The same is not true here. It is memoryless because yn at any instant, the output at any instant, nth instant is a function of input at previous instant. There is n minus 1th input. So it has a memory. Just like a flip flop has a memory, delay flip flop has a memory. So it has a memory. Similarly, this is also not memoryless because yn, the output at nth instant, is a function of input as well as the output at the previous instant. It's a sequential system. It's an example of a sequential system. So how? Say sorry, this yn minus 1 can be written as replacing n by n minus 1, x of n minus 1 plus y of n minus 2. Again, yn minus 2 will be x of n minus 2 plus y of n minus 3, and so on. So finally what you will have is xn, xn minus 1, xn minus 2, and finally this. So obviously you can see that the output at any instant n, that should be n obviously, sorry, will be a function of the input signal starting from minus infinity to that instant. Correct that, I don't know that we'll be able to correct it. Okay, I'll correct it later and I'll send you. Okay, this should be n. The upper limit should be n. So that is a system with memory and memoryless. Now invertible. When we call a system to be invertible, if every distinct input produces a distinct output, or in a sense there is an one-to-one correspondence or one-to-one mapping between a set of input signals and a set of output signals, then we call that system to be invertible. That is, given input we can find out the output, and vice versa. That is, if we know the output, then we can find out the input following the mathematical description of the system, where there is a one-to-one mapping between a set of input and corresponding output signals. Say example, suppose the system yt is given by cos t plus 2 into xt. It is invertible because given yt, you can calculate xt as yt by cos t plus 2, right? So given an input, you can calculate output, and given an output, you can find out the corresponding input. Then this system is also invertible because you can represent yn as a function of xn and yn minus 1. Similarly, given an yn, you can find out xn as yn minus yn minus 1. So it's invertible system. Fine. Let me get back. What about this system? Yt equal to x squared t? It is not invertible. Why? Any idea?
So this is not one-one function, sir. It is one-one mapping.
There is no one-to-one mapping because x1 equal x1t of minus is not coming. This should be minus. Minus 1 and plus 1 will both lead to yt equal to 1. But clearly, x1 and x2 are not equal, so there is no one-to-one mapping. So it is not an invertible system. Okay, the minus n is not coming on to y. So two different input signals will produce the same output. So we cannot predict from the output what is the input signal. That is why it loses invertibility. Fine. Then causal. I've already mentioned that if the output at any instant of time depends only on the input at that time or previous instant of time, then it's a causal system. Otherwise, it's a non-causal. Suppose this is a causal system X, because output at nth instant is a function of input at n minus 1th instant. So it's a causal system. This is a non-causal system. See, yn equal to xn plus x of n plus 1. Right. So output at any instant, the nth instant, is a function of input at that instant n and the input at n plus 1th instant, which is a future instant of input. So obviously is a non-causal operation. So we cannot say this is a causal system, rather this is a non-causal system. Now let us take an example where we have write down to tell me whether this is a causal or non-causal. Whether it's causal or non-causal. Yes. বলো এটা কজাল না নন কজাল?
স্যার আই মিন এটা কজুয়াল হওয়া উচিত,
Causal.
টাইম ডিপেন্ডেন্ট হচ্ছে স্যার, টাইম ইনভ্যারিয়েন্ট তো নয় এটা।
No, see, I already mentioned this distinctions, this classification is entirely independent. Forget about time dependent or time invariant, whether it's causal or not. See, the integration is from minus infinity to t. There's the instant of time at which you're interested about the output, and the input that is considered here is from minus infinity to t. That is all the inputs from present and all the past inputs only. So it's a causal system, right? There's no need of any future input. So it's a causal. Just think about the inputs that you require, not about the any other property. Then what about this? Causal or non-causal?
So it's a non-causal system
Why?
because the input depends on the future inputs, that is t plus 1.
What is this function? This is cosine of t plus 1. No, it doesn't depend on the future value of input. At any instant of time t, we
স্যার
just
অ্যাকচুয়ালি উই ক্যান,
we
আই
have to
মিন
just calculate the cosine of t plus 1.
t plus 1, yes sir,
So it is
exactly.
obviously a causal function. See, that is why I've given this example. Whenever you see a plus 1, it doesn't mean it's a future input. It's a mathematical function where it's a function of t plus some variable 1. Had that been x of t plus 1, then it could have been something else. Say that x of t may be some t plus 1 whole square and things like that. That's not that. It is a cosine function. So it's a causal. It depends on the value of xt. That is the important thing. What type of input, what instant of input you're dealing with? You're dealing with the present input, but it's a time varying system, right? For different instance of time, you will get different value of yt for same xt, because this coefficient is time varying. And how it is time varying? In a cosine manner, cos of t plus 1, which is just a numerical value. It's not dependent, it's not a future value, it's just a numerical value based on the time of t. So it's a causal system. Understood? What about this sequence? Causal, non-causal? কি বলবে এটা?
নন কজালি হওয়া উচিত, মানে
কেন
ফিউচার
বলছো?
ডিপেন্ডেন্সি তো
এটা
চলো n
causal.
equal to 1, তাহলে তো y1 equal to x of minus 1
মাইনাস 1,
ফার্স্ট, কোনো অসুবিধা নেই। সো ইউ ক্যান সে যদি n equal to -1 হয়,
দেন ওটা ফিউচার হয়ে যাবে।
দেন ফিউচার হয়ে গেল।
হ্যাঁ, মানে এন এর একটা
ওইটা
মানে
non-causal।
এটা কজাল নন কজাল দু রকম হলে ডিপেন্ডিং অন দ্য
Exactly.
ভ্যালু অফ
For
এন।
n greater than equal to 0, causal, n less than 0,
নন কজাল হয়ে যাবে।
কখন n less than 0 হতে পারে বলো তো? n greater than 0 আমরা তো জানি, এটা সিকোয়েন্স 0 1 2 করে আমরা গুনি, তাই তো? তখন less than 0 হতে পারে। হতে পারে কি কখনো? আবার ফিরে আসো। আমরা যখন ছবিটাকে when you are analyzing this image, started this as your reference, right? X equal to 0. Now if you start
আচ্ছা, আপনি রেফারেন্স লাইনটাকে আগে এগিয়ে দেবেন।
exactly from x
আচ্ছা,
equal to 50, so this is your reference. So this is n greater than 0, n less than 0, right? And this is n equal to 0. Just shifting of axis, right? That's for analysis purpose. If you get a symmetric image, and you find out the axis of symmetry, then we normally take that axis of symmetry as reference and move in either side. তোমার তাহলে এটা কমে যায়, কম্পিটিশনটা কমে যাবে। So in that case, you can have n greater than 0, n less than 0, right? So this is how a causal system can be identified or described. Very good. Let us move on. এগুলো এখানে করা আছে। So next property, stable system. So the stability that we are discussing about is a Bibo stability, that is bounded input, bounded output stability. So to describe a system, we need to first define the boundaries of the signal. That is, given a signal input xt or xn, say it is bounded by some finite value b such that mod of xt is less than b for all t. Then the system will be stable if this bounded input always produces a bounded output. That is, for xt less than equal to b, for some b less than infinity, then yt should also be less than infinity. Then you say the system to be bounded input, bounded output stable, or Bibo stable. Say this is a system and we are dealing whether this system is stable or not. আচ্ছা এটা বলো তো, এটা দেখো yt equal to 2x square t minus 1 x sub 3t, এটা কি causal না নন causal? এটা causal না নন causal?
স্যার এক্স স্কোয়ার টি মাইনাস পাসওয়ার্ডের উপর তো ডিপেন্ড করছে, এখানে তো আমি চেঞ্জ করতে পারবো না। টি মাইনাস ওয়ানটা এখানটা
এটা ঠিক আছে, এই ফ্যাক্টরটা দেখো 3t আছে, 3t
রেডি আছে,
নন
মানে এটা
causal,
তো
t equal to 1 বসালে এটা হয়ে যাবে 3,
কি হয়ে যাবে, ফিউচার
তাহলে
হয়ে যাচ্ছে।
ফিউচার, তাহলে নন causal সিস্টেম একটা, রাইট?
হ্যাঁ,
So consider a bound like this xt less than b. Now you take a mod of yt, so that is mod of 2x squared t minus 1 plus x sub 3t, and we know xt is less than b for any value of t. So we can simply write this mod is less than equal to mod of this plus mod of this, right? দেখতে পারি again by definition this is less than 2b square and this is less than plus b, and since b is finite, so this is also finite, less than infinity, so yt is also bounded by some finite boundary, 2b square plus b. So you can say this system is a Bibo stable system, right? This is an example of a Bibo stable system. Okay, let's take an example of a unstable system. যেমন করছি করে নি, suppose our discrete time system is given as yn is equal to, এটা আমরা করলাম একটু আগে, যেটা ফার্স্ট আমরা দেখছিলাম, একটু ফিরে যাই। সরি, এই সিস্টেমটা yn equal to xn plus yn minus 1, বেসিক্যালি আমার ইকুয়েশনটা ছিল yn equal to xn, এটা ছিল সিস্টেমের ইকুয়েশনটা, সেখান থেকে আমরা পেয়েছি yn is something like this. Now you have to study whether the system is stable or not. So for that, say your xn is equal to un, that is unit step sequence, that is un equal to 1 for all n greater than equal to 0, right? So obviously you can write that mod of xn is less than equal to 1 or bounded. Now you have to show whether the corresponding yn is bounded or not. So take mod of yn, so it will be mod of infinity to n. Xk can be written as now uk. So since uk is always greater, so mod goes out, so k equal to minus infinity to n, and UK, and that is less than equal to, right, because un is bounded by 1 for all n greater than equal to 0. So it is only present for k equal to 0 to n. So what will be this value? N plus 1. So we can say the boundary that you found out, yn is less than equal to n plus 1.
স্যার এই স্টেপটা আরেকবার একটু বলুন এই
এটা
হ্যাঁ ওই স্টেপটা হ্যাঁ
uk is equal to 1, so it is obviously less than equal to 1 ধরতেই পারি, যেহেতু আমরা xnটাকে ধরে নিয়েছি বাউন্ডেড বাই 1, ইকুয়াল টু 1 ধরতেই পারি, ঠিক আছে, ইকুয়াল টু নিতে কোনো অসুবিধা নেই। So it is always bounded by 1, and এখানে সিকোয়েন্স কি minus infinity to n, but this un is only present for n greater than equal to 0. That's why limit is changed from 0 to n,
আচ্ছা আচ্ছা
and uk is replaced by 1. তাহলে n times যোগ করবো, এখন n plus 1 পাবো। So yn is bounded by this. So this is the boundary on the output, provided the input is bounded by unity 1. So এটা বলো, এটা bounded না unbounded? এটা
সেটা আনবাউন্ডেড।
yes, as n tends to infinity, mod of yn tends to infinity. So it is not bounded. So you can say this system is not Bibo stable. গেল, তাহলে কি হচ্ছে, yn তুমি যত n বাড়াতে বাড়াতে যাচ্ছি, the output is getting increased continuously, so it is obviously not bounded. I think last two very important properties you need to check, and that will be the class today. Time invariancy. So a system is time invariant if a time shift of the input signal results in the same time shift of the output signal. And output, there is no change in the nature of the output. That is, if xt yields yt, then xt minus t0 will yield yt minus t0 for any t. Example, suppose we have yt equal to sine of xt, and we call this time invariant. দেখো এটা কিন্তু একটা non-linear function. Okay, it's not a linear function. So what is the time, say at t minus t0 or we're having a new input signal x1t, which is the time shifted version of the input signal xt, and time shifting is by amount t0, so x1t is equal to x of t minus t0. Now correspondingly the output with respect to this x1 will be y1, where we put x1t sine of x1t is y1t, that is sine of x t minus t0. Fine, so this is your output with respect to this new input x1t, where t is replaced by t minus t0 to indicate there is a shift in the input signal. Now what about the output signal? If we just consider this output signal y1t, if we put a time shift of t minus t0, we have to show whether that shift in the output signal, that is yt minus t0, whether it is equal to the output due to the shifted input or not, right? So output due to the shifted input is this, and now we have to show that if we shift the output, the original output by t0, the signal is yt minus t0, so whether they are same or not. If they are same, it's time invariant. If they are not same, then it's a time varying. So এখানে মাইনাসটা পড়েনি কোনো কারণে, so t minus t0, y of t minus t0, which is equal to sine of x t minus t0, which is same as the output due to the shifted input. So it's a time invariant system. বোঝা গেল লজিকটা? এটা কমপ্লিকেশন হলো কি? আচ্ছা আমি বলে দিচ্ছি তাহলে। চেক করার লজিকটা বলছি আর কি। সে for xt your yt is defined as sin of xt. Now we define an input x1t which is x of t minus t0. So corresponding to that, what will be the output? Say y1t sin of x1t from this function, and that is equal to sin of x t minus t0. Now if we consider the time shift, how much shift we have considered? The same amount of shift by which the input is shifted. Now we have to check whether this y1t is equal to yt minus t0 or not. In this case, see y1t and is the same, so it's a time invariant system. ঠিক আছে? আরো ক্লিয়ার হবে যখন আমরা এইটা করব। সাপোজ for given xt your yt is defined as t sin of xt. Let us check, and we have given an input, say x1t is defined as x. So what will be the output? Yeah, bolo. Right? So t sin of x. So this is your output corresponding to this time shifted input. Now from yt,
So ওটা t minus t0 হলো না কেন, মানে
বলো
লিডিং টিটা মানে t sin x of, আচ্ছা আচ্ছা বুঝতে
yeah, t minus t0. Now if we apply time shift over here, সেটা কি হবে? Replace right? So clearly in this case you can see that y1t is not equal to y of t minus t0. That is, the output due to the time shifted input x t minus t0 is not equal to the time shifted output y t minus t0, because এখানে আছে t minus t0 আর এখানে আছে t, right? So this is a time varying system. বোঝা গেল?
হ্যাঁ স্যার।
Okay, very fine. And finally, we have the most trivial of this, the linear system. If it is additive and scalable, then we call it linear system. And suppose x1 and x2 yields y1 and y2, then ax1 plus bx2 should yield ay1 plus by2 for all a and b. That is a linear system. Say this system, how it can be shown that it's a linear system. Take a signal yxt defined as ax1 plus bx2, where y1 is output due to x1, that is 2 pi x1, and y2 output due to x2, that is 2 pi x2. Then we have to show that a y1 plus by2, that is a 2 pi x1 plus b 2 pi x2, that is equal to 2 pi, common now, ax1 plus bx2, that is 2 pi. What is ax1 plus bx2? Equal to xt. There's a new input signal that you have considered here, right? So that is your yt. So you can write, sorry, so you can clearly, write that I don't know, that this system is a linear system, right? So an example of a linear system, say we have considered, sorry, এটা দেখাই যাবে না, yt is equal to 2 pi xt, right? And now you have considered two input signals, x1t that produces an output y1t and x2t pi x2t. So we have to show that say this is defined as an input x bar t and it produces an output say y bar t. So we have to show that the y bar t is equal to a y1t. Then you can say this is a linear system. And if it is not, then it's a non-linear system, right? So this is how you can classify between a linear and non-linear system. I think this is very trivial, right? This এই চেকটা তোমরা আশা করি করতে পারবে, ঠিক আছে? যেটা মোর ইম্পর্টেন্ট, যেটা আমার মনে হয় দিয়ে আছে লেকচারটা শেষ করা উচিত, সেটা হচ্ছে we have discussed about different classifications and I have intentionally left one classification left of it, and that is, you can say, can be clustered in any of the classification, that is dynamic system. And আর যারা স্ট্যাটিক লেখে, আমি স্ট্যাটিকের থেকে নন ডাইনামিক টার্মটা বেশি প্রেফার করব। Non-dynamic system, right? So any idea what is a dynamic system and what is a non-dynamic or static system? Anybody? এটা কি আগে কিছু বলেছিলে বস্তু?
মানে প্যারামিটার গুলো অ্যাট এনি পয়েন্ট চেঞ্জ হতে পারে।
স্যার ওটা যেটা আগের দিন বলেছিলেন যে ডায়নামিক সিস্টেমে ট্রানজিয়েন্ট একটা স্টেট
Exactly.
থাকবে।
ঠিক, এই এক্সাম্পলটাই মানে দিয়েছিলাম। যদি সরি ঠিক হলে যে সুইচটা আমি ক্লোজ করি, তাহলে আমার ইনপুট সিগন্যালটা পড়ছে ভি, আর আউটপুটটা আমি পাবো সেম। What is the output? The output is but that is it is a Static system, instantaneously the output change follows any change in the input. And for a dynamic system, suppose we have a this is the output. So in that case, what you'll have, or input will be something like this, but our output is the input. At t equal to 0, it takes a value v. The output will be something like this. Sorry. And normally, this period is called the transient period. And how do you define this v0? Right? So, see, in this case, the v0 was IR as an algebraic equation. And in this case, 0 is a integral differential equation. Integral equation, it might be in some cases differential equation as well. So this system is a dynamic system. So in next class, so this is a broad classification. Any system, whether it's a linear, non-linear, continuous time, discrete time, time invariant, time varying. Obviously, there's no time invariance in a static system, because in other case you can also say the static system has no memory, doesn't depend on a memory. It's always causal, right? And it may be time invariant or maybe time varying, because if the value of the resistance changes with time, then it will. In this case, always it is in this case. Obviously, the voltage will always be V. There is no change, but the current value, if you consider the current value, so that might change. Say if we draw the current, so that current value will change, right, depending upon the value of R at different instant. If it is variable, but the output will be 0. Fine. So there's always the time dependence like that. And the dynamic system, as I already mentioned in the last class, most of the physical systems are dynamic in nature because of the inertia that they have. They tend to retard any change in its condition or state instantaneously. So it will have to pass through a transition period, which is called a transient period. And that's why all the dynamic systems are described in terms of linear differential equation. Okay. So in the next class, we shall discuss about basically how an LTI dynamic system can be described in terms of differential equation or integral differential equation, and then how to analyze those systems with the help of some mathematical tool. So as a mathematical tool, a very strong mathematical tool, we shall mainly discuss on Laplace transform. So those who have a brief introduction to Laplace transform, please try to recap those and try to recap as much as you can as much as possible, so that we can pass through the initial phases of the Laplace transform and its properties very quickly. Then we'll see how this dynamic equations can be solved to get the output for different types of input using Laplace transform technique. Right? So I'll not develop dynamic equation for a particular system or every type of systems. That is a part of other part in the syllabus of other part. So I'll consider a dynamic equation or a differential equation and try to show you how we can solve the differential equation using Laplace transform technique under different conditions, right? So with this, I'll conclude the class today. So if you have any query. ফাইন। আচ্ছা, একটা ব্যাপার, আমি নেক্সট স্যাটারডে হয়তো ক্লাসটা নিতে পারবো না, আমি স্যাটারডে থাকবো না। সো ইন দ্যাট কেস ক্যান ইউ প্রিপন ইট টু ফ্রাইডে, দ্যাটস 26th, সেম টাইম?
সেম টাইমে পসিবল হবে না স্যার, অ্যাকচুয়ালি উই হ্যাভ ক্লাসেস ফ্রম 11 স্যার।
এই ফ্রাইডে 26 ছুটি গো।
ও সরি 20, আচ্ছা আচ্ছা 26 পড়ছে, আচ্ছা আচ্ছা, হ্যাঁ তাহলে হতে পারে।
ঠিক আছে, তাহলে আমি একটা অ্যানাউন্সমেন্ট করে দেবো। ঠিক আছে, সো কারণ স্যাটারডে আমি থাকবো না 27th, দিস উইক আই উইল টেক দ্য ক্লাস অন 26th।